Let me repeat that part, by the way, for everybody. We're talking about Darlington pair, and the whole idea of Darlington pair is to come up with a good transistor, like somebody call it a super transistor. We need to have a super transistor. What would be a super transistor? A transistor with a very high beta is a super transistor. Usually beta, the order of magnitude of beta is 100, 200, 300, something like that. A super transistor means we like beta to be much higher than that. To be much higher than that. It could be 1,000, 10,000, something like that. So we reached the conclusion here that a super transistor made of a Darlington pair, beta of the combination is beta 2 times beta 1 plus 1. Roughly, it's like beta square. So if beta is 100, then the super transistor would be like 10,000, something like that. Advantage of having high beta is that this transistor doesn't consume too much current from the power supply, doesn't consume too much current from the surrounding circuit. This is an example, and I have gone through this example before. When we were designing like audio amplifiers, sometimes we designed, by the way, very beautiful audio amplifiers on this campus. There was usually something called an E-Day, you know, the E-Day, engineering day. And we bring the parents of the students and all of that, and they watch what their what their children are doing in classes. So we demonstrated a lot of good instruments, let's put it this way. Believe it or not, instruments, although they were students, but it was up to the level of professional engineers in my own judgment. Here is an example of a Darlington. The necessity of Darlington pair here is obvious in this example. If you want to feed a speaker by a single transistor like this, it doesn't work, because the speaker usually has an input resistance of 4-8, from 4 to 5 to 6 to 7 to 8 ohms. Yeah, very, very small resistance. That means it will take a high ampere. It can pass a high ampere, AC and DC also. That's how the speaker works. Let us assume that we're talking about 1 ampere. If you divide that by 100, you're going to get 10 milliampere here for biasing. And then if you need to provide 10 milliampere here, there is a rule of thumb, by the way, which is not written in the books, but it is well known by design engineers, analog engineers, analog designers, which is that the biasing current should be at least 10 times as much as the current you're trying to draw from that point. So if you're trying to draw 10 milliampere from that point, the biasing current should be 10 times as, at least 10 times as much as that, which is 100 milliampere. 100 milliampere is a big amount of current. Typically, 100 milliampere, you could run so many things with 100 milliampere. Much more sophisticated applications. Big circuit can run with 100 milliampere, but not a single transistor. Single transistor is usually talks about few milliamperes. So our duty as designers now is to reduce the amount of current drawn from this biasing arrangement. So we're going to have a Darlington pair here with a super beta. Beta could be like 10,000, 100 times 100, approximately 10,000. So if you draw a 1 ampere here, you're going to draw 10 milliampere here, you're going to draw 0.1 milliampere here. It boils down to this. You need to draw 0.1 milliampere here, which is okay, because that will necessitate or require or entail, I'm giving you different words that you can use in formal reports. There are some words which have close meanings, not identical. There is no two words which have the same meaning. There is always a hair thin of difference between the meanings. But you can say, okay, this is 10 times as much at least as 0.1 milliampere. So you need 1 milliampere here in this arrangement, which is reasonable. If you want to draw 1 milliampere here, that's very reasonable. So this biasing arrangement works. This biasing arrangement is poor design. This one at the top here is a poor design, and we should avoid things like that. So this is a good example to show the importance of Darlington pair. This is a very good example for using Darlington pair. Let me move to the second part of this chapter, cascaded amplifiers. As I said, you will not find this kind of classification in the book, but that's my own classification. I classified this chapter into Darlington pair, then cascaded amplifiers, then emitter couple pair. All right. So here is an example of a cascaded amplifier. We have a 3-stage amplifier. Let me ask you this. Suppose I tell you we need to design an amplifier with a gain of 1,000. Well, some people are gonna do this. You're gonna say, okay, 10, 10, 10. So 10 times 10 times 10 is 1,000. But when you go to the lab and measure the gain, it turns out not to be 1,000. It turns out to be 600, for example, or 700, or something like that. So where is the problem coming from? Did we do bad design, or What is it exactly? There is a common fallacy or a common, there is a rumor among students that theoretical performance is something and practical performance is something else. I would like to tell you this. Theoretical and experimental response are identical. It doesn't make sense to say that there is one response that does not belong to the other response. They are identical, except that our interpretation is